Welcome back. In this video, I'm just going to cover a couple more examples of how to work with line integrals. As I mentioned in my last video, we're going to do one with an ellipse, one with a circle, and then one that's a little bit more complicated and requires to be broken down into multiple different pieces. So let's go ahead and recap what the line integral is, and then we'll jump right in with that ellipse example. So line integral, how do we work with it? Well, it's really just we're taking the integral of a function and we are restricting that integral to working with a curve C. So instead of integrating over a area or volume or something like that, we're just looking at like a line segment or a kind of a wavy line or something like that. And the way that we handle these kinds of integrals, a really nice setup for that is going to be to parameterize your curve C with R of t, plug that curve into f to restrict f down to that curve, and then multiply by the derivative to, do the whole change of variables, u sub type thing. And then your bounds on this become the really nice and easy to use a to b, which are based off of your t there. So much easier to integrate. At that point, you can just use fundamental theorem of calculus. Is pretty straightforward. So let's go ahead and jump into the ellipse example. So for this one, we're going to have f of xy be equal to xy squared, and our curve C be given by x squared over 16 plus y squared over 9 equal to 1. And we are going to find the line integral for that one. So integral over C, f of xy ds. So that is a comma. Okay, so the first thing we have to do is, parameterize this ellipse right here. So just kind of remembering back what that parameterization looks like. We want to take the square root of the bottom here, and it gets multiplied by cosine of t for x, and then same idea here, but sine instead for y. So r of t is equal to, it's going to be 4 cosine of t replaces the x, and then 3 sine of t replaces the y. And in this particular instance, since we are creating an ellipse, which goes all the way around, we are going to want t to be between 0 and 2 pi. The derivative here is going to be equal to, it's the derivative of this guy right here. So we're going to get negative 4 sine of t, and then 3 cosine of t. So then our length is going to be equal to square root of 16 sine squared t, and then plus 9 cosine squared t. All right, so now all we got to do is plug in our different pieces into this expression right here, and we'll get the whole integral. So, our integral over the curve of xy squared ds is now going to become the integral from 0 to 2 pi. And then I have to swap out my x and y squared for what I found here. So I'll have 4 cosine of t times 3 sine of t squared, and this is, I'm going to run out of space, times the square root of 16 sine squared t plus 9 cosine squared t dt. Okay, this is all in the same integral. I just ran out of space here at the end. This winds up being your final answer. I guess you can simplify that a little bit. And I suppose you could throw this into like an integral calculator if you wanted to, but this is really quite messy to try to do by hand. In fact, I'm not really entirely sure that it would be possible to do it by hand, just simply because you can't combine the sine and cosine here because of the 16 and the 9 being different there. So you can't use the nice trig identity there. So I do want to note that you're not going to evaluate this. And this was something that I pointed out in my previous video. If you hit something that looks really messy like this and you have no clue how to integrate it by hand, always go back and double check your homework instructions and make sure that it actually tells you that you should integrate it, or, tells you to find the integral specifically, and that it doesn't tell you to not integrate. And a lot of times when you get something like this, the instructions will actually specifically tell you set up, but do not evaluate. And that's what we're going to see here, is that we're really not going to evaluate this. We're just going to leave it as it is, and that's fine. All right, let's do an example with a circle. It's really quite similar. So for this one, we're going to find contour integral or line integral of x ds, where our c here is given by the circle x squared plus y squared equal to 9. And it's actually going to be a half circle because we're going to require x to be positive. Okay, so we remember that line integral, we want to break it down into an integral from a to b, f evaluated on a parameterization of our curve times the length of the derivative of that, dt. And so we have to parameterize this guy right here, come up with bounds, plug it into f, and then integrate. So parameterizing in circles is pretty straightforward. We're going to use the sine and the cosine, r cosine t, r sine t stuff, and you get r of t is equal to 3 cosine of t, 3 sine of t. And I'm just going to go ahead and note right now, this piece is our x, that piece is our y. We take the derivative, and we get negative 3 sine of t, 3 cosine of t. And our length then is really just going to be 3. Okay, so now the tricky part becomes, okay, what are my bounds for t? And to get those, I'm going to sketch my region here, or my curve, to see what we're looking at. This is a circle of radius 3, and we only want the right side of it because we want x to be positive. It's going to look something kind of like that. And now, as soon as we've swapped over to this parameterization with the sine and the cosine, we're thinking about t as being an angle. And if we're looking at this as kind of like a theta type deal, we're going to be going from negative pi over 2 up to pi over 2. So then I need t to be between negative pi over 2 and pi over 2, just like so. And those are going to be my bounds for t. So now I'm ready to go ahead and plug everything into this integral right here. So I have the integral from negative pi over 2 to pi over 2. My x here is going to become 3 cosine t. This piece here is going to be 3, and then I just have dt. So that's equal to 9 integral from negative pi over 2 cosine of t dt. And that's all there is to it. This is a really very easy integral to take, so I'm going to leave that to you guys to work out, but it's really quite straightforward, and yeah, that's a simple integral. So you should definitely work this one out. But yeah, that's all there is to this example. All right, now I have my one last example, and this one's a little bit more involved. So for this one, what we're going to do is we're going to still find a contour line integral. And f is going to have kind of 4 different values that it takes on. When it's in the first quadrant, it's going to be equal to 1. In the second quadrant, it's going to be equal to 2. In the third quadrant, it will be equal to 3. And in the fourth quadrant, it is equal to 4. And the curve that I'm looking at in this case is going to be a square that has its center at the origin, with one of the sides being along the line segment 2, negative 2 to 2, 2. So, all right, let's unpack this a little bit. But I guess before we do that, we should probably remind ourselves that first and foremost, our goal is to take that line integral and rewrite it in terms of a parameterized version of it. Okay, so this is our ultimate goal, is figure out how to decompose it into something that looks like that so we can take an integral. Now, let's see what on earth is happening here. I'm actually going to go ahead and graph this square so that way I can kind of use that to keep track of what f is doing. So, all right, let's get some color. Okay, so so it has a side that goes from 2, negative 2 to 2, 2. So I'm going to mark all the 2's around here. And so our square is going to do something kind of like this. It has our center at the origin. The side goes along all those twos like so. So there's our square. This is our curve C that we are interested in. Now, let's figure out what F is doing in each of these areas here. So if we're in the first quadrant, that's going to be this guy right here, right? So F is equal to 1 right there. So that's the value that I would put down for F. In my second quadrant, though, F is going to be equal to 2. In the third quadrant, F is equal to 3. And in my fourth quadrant, F is equal to 4. So I have 4 different rules, 1 for each quadrant. So that in and of itself tells me that I'm already going to need at least 4 different integrals because F is following 4 different rules depending on where it's located. So And so, okay, it's going to be tempting to go ahead and be like, okay, I'm going to split this into 4 pieces and then I'm going to be done with it. However, notice that in each quadrant, our curve is following 2 separate rules, okay? In each quadrant, I can think about each curve as having 2 pieces. So like in my first quadrant, this curve is a vertical curve and a horizontal curve. Call it C1 and C2. In my second quadrant, I've also got a horizontal curve and a vertical curve. Call it C3. And C3 is going from right here to right here. So from 0 out to -2. And then C4, same idea, like so, okay? Similarly, we can label the other pieces of this curve in the other 2 quadrants. In the third quadrant, I've got a vertical piece, call it C5, and a horizontal piece, call it C6, and then C7, and C8. So I can really think about this curve as actually kind of having 8 different pieces to it. So in each quadrant, C has 2 separate line segments. And we need an integral for each one of these too. So we're going to ultimately need 2 integrals per quadrant. And what this means is that we now have to split up our integral that had been so nice and tidy and just, you know, an integral over a curve of F. We need 8 integrals. So one for each one of these little segments here. So yay, lots of fun. What that's going to look like is really we're going to take that curve, the integral over that curve f ds, and I'm going to write that as the integral over C1 f ds plus the integral over C2 f ds plus the integral over C3 f ds plus the integral over C4 f ds plus the integral over C5 f ds plus the integral over C6 f ds. Oh, and 2 more. Integral over C7 f ds plus the integral over C8 f ds. And honestly, if we wanted to, we could go through and replace those with the values for f. Looking at this picture here, when we're in the first quadrant with C1 and C2, f is really just equal to 1. And when we're in the second quadrant with C3 and C4, f is just equal to 2. And we're in our third quadrant with C5 and C6, f is equal to 3. And when we're in our fourth quadrant with C7 and C8, it's equal to 4. So you can go ahead and put those down like that if you want to. All right, so what we've done is we've taken our integral and we've broken it up into 8 different little pieces there because we are allowed to take the curve, break it up into pieces, and then add all the pieces up at the end to give the result that we want. So I'm going to work one of these and then I'll leave the other 7 to you, but they all are exactly the same. So here's our little example one. C1 is the line segment from 2, 0 to 2, 2. Okay, so let's go back and look at our picture that we drew. I highly recommend that you draw pictures for these kinds of problems when you can, because it just makes it a lot easier. So this point right here is 0, 2. Oops, nope. 2, 0 for this point right here, and it goes up here to 2, 2 is what C1 does. So that's this line segment right here. We need to parameterize that. So C1 is equal to R of t, which will be equal to, after it's parameterized, 2, 0 plus t times 0, 2. So my derivative, R prime of t, is equal to 0, 2. And my length of that is just equal to 2. So, again, t, when we're working with the line segments, is between 0 and 1. So the integral over C1, 1 ds, because remember that we have 1 there for my value of f, that's equal to the integral from 0 to 1 of 1 times 2 dt, which is just equal to 2t evaluated from 0 to 1. That's just equal to 2. So that's really, like, this little piece here isn't so bad, and actually parameterizing isn't so bad. It's just that you have to go through and do it for each and every single one of those. So apply the same process to the other 7 integrals, and then you add all the pieces together at the end to get the total. Once again, I will leave all of that to you to work out. But again, it's not terribly hard as long as you follow this setup right here. For each one of these here, none of the integrals are tricky. They work out quite nicely. So you should get really nice numbers at the end for that. So, but yeah, that's 3 more examples for you. Hopefully this has been, well, helpful. And yeah, that's pretty much it. So thanks, guys. I'll see you.